So I'm Freddy Cachazo, and I'm in charge of finishing a very exciting course, right, in conformal field theory, which is basically a set of 3 courses. So that's why I decided to call this Conformal Field Theory 3. Okay? So in the first 2 weeks, I tried to see what you guys did with Jaume and Pedro, and I realized that you guys did very exciting things. Now, I'm afraid that this week it would look a little bit boring for you, okay? Because we are mainly going to go back in time, okay? So you have been discussing conformal field theories in dimensions greater than 2, where many exciting developments have been going on. And Pedro, I'm sure he made references to papers from 2011, 2012, and even things that happened this year. And I'm afraid that I can only offer a paper from 1991. And the goal, really, is to use this paper in order to be able to understand the classic work from 1994. Okay? But, well, sometimes that happens. And the goal of the lectures, then, is to do conformal field theory in the equals 2. Okay? So even though this sounds very, very old, I mean, especially given that many of you were probably born around that time or even later, it turns out that, 84 is not that old. And the whole subject really started to pick up and was developed after this paper. So this is a landmark paper. And even though many, many people have worked on conformal field theories in 2 dimensions and lots of things are known, there are also open questions. And usually, even if you think that something has been going on for a long time and you say, well, thousands of people have looked at this, sometimes people stop looking at it to find new things. And so don't be afraid to jump into a field that has been going on for a while, because maybe you will come out with a new insight that people just stop looking at it, okay? And especially when you look at a field and it's new to you, it's the best time for you guys to ask the questions that nobody had come out with, even in many, many years, okay? So why D equals 2? Well, the first reason is that, well, I've been debating about which one should be the first and which one should be the second. But, okay, but let's do the standard one, and then you will see why I've been debating about what is the first and what is the second. So the first one is to describe the critical behavior. And I'm doing it just because Kiefer is here. If he wasn't here, I would do something. I would do it in the other order. Describe the critical behavior of systems at second order phase transitions. Okay? Well, in other words, we want to study this because the range of applications in statistical mechanics is incredible. Okay? Many things that were possible only before in approximations became exact calculations. Calculations of critical exponents became possible. So it was a whole revolution around the 80s. Okay? And, of course, the canonical example is the IC model. And I know that with Pedro, you basically solved the IC model in 3 dimensions last week. So it would sound boring to go back to 2 dimensions. But I think you couldn't actually find the critical exponents all the way. You just found some approximation to the critical exponents. But in 2 dimensions, we're going to be able to find exactly what they are. So that's my excuse for doing the IC model. Now, the second reason, and I think we lost part of the structural integrity of the blackboard. Huh. That doesn't quite work. Okay. Yeah, we need more weight there. Okay. So I need a loonie from each one of you. Every lecture. Okay, so the second motivation, of course, and now you're going to see why I debated, is a string theory. So conformal field theories in 2 dimensions lie at the heart of a string theory, okay? Or at least in the formulations that we have understood well. So a string theory is based on the idea that we have one-dimensional objects moving through space-time, and we define a conformal field theory living on the worldsheet. And you would say, well, why is a conformal field theory important? Well, the reason it's important is that it's precisely the fact that this is a conformal field theory that allows the theory to evade all the UV divergences that appear in any approach of quantum gravity that you try, especially just standard quantum gravity. If you try from the Einstein-Lagrangian, you will find that even by adding supersymmetry to the Einstein-Lagrangian, you will find UV divergences at some point. Well, some people believe that maybe if you add enough supersymmetries, the theory might be finite, but that's very unlikely. I think most people think that even if you add the maximal amount of supersymmetries to supergravity in 4 dimensions, the theory would still be UV divergent, even though the divergence will probably appear at 6 loops. So if you are brave enough to go all the way to 6 loops, you will probably find the UV divergence. So far, we believe that the trick for evading UV divergences and thus having a consistent theory of quantum gravity lies at the heart of these conformal field theories living in 2 dimensions, which translate all UV divergences into infrared divergences. But for that, you will have to wait until Davide Gaiotto teaches string theory in February, I think, right? All right. So that was a motivation. Now, what are the things that I'm going to assume? So I'm going to assume that you're all experts in the conformal group in D greater than 2 dimensions, okay? So every now and then I will ask one of you to come and do things on the blackboard. Is that okay? Come on, give Freddy. Somebody told me you have been following all the lectures, so you should be able to come to the blackboard. Okay, so this is something I'll assume. What I won't assume is that we're going to study the conformal group in D equals 2. So instead of reviewing what you guys did, I'll just jump to D equals 2. So most of today's lecture is going to be a little bit boring, I have to say, because it will mainly be translating things you did in D greater than 2 to D equals 2. And it's just going to be a translation of languages, because in D equals 2, we're going to use complex analysis. So we're going to translate all the tensor structure and all that into the language of complex variables. And that would take a while, I'm afraid. So we will just have to get it done, and perhaps tomorrow we can start with more exciting things. So if you get bored today, that was intention. So I'm afraid there is nothing I can do. So we're going to start with an Euclidean space-time. So this is an Euclidean space-time. So it's just R2. So the metric, we have to give some name to the coordinates. So I'll probably be very inconsistent with the name for the coordinates. But I guess in this page, I call them x1 and x2. So the metric is just x1 squared dx2 squared. And now you see why it's very tempting to introduce complex coordinates, right? Every time you only have two squares, it's begging you to introduce complex coordinates. Right? And therefore, the differentials are just the same. And the reason we all know that this was a good idea is that the metric is going to have a beautiful, simple form. Okay? Now I want to find the components of the metric. Okay? So what is a metric in these coordinates? So our metric, of course, is a 2 by 2 matrix. So let's see, what are the components of the metric? Exactly. 0, half, half, 0. Is that clear to everybody? Excellent. Very good. Now, any questions? No? Excellent. So, in the past 2 weeks, you have been looking at conformal transformations, right? Coordinate transformations that modify the metric up to an overall factor, which is called the scale factor. So here we see that there is a very simple way of producing a conformal factor. We just simply take z and replace it by any function that is meromorphic in z. Okay? Any meromorphic function will do. What's the difference between meromorphic and holomorphic? Well, meromorphic, I'm allowing for something that could possibly contain poles, right? But it's only a function of z. It's not a function of z bar. So under this transformation, what happens to our metric? Where our metric goes into right? So this object here is nothing but the mod square of the derivative of the function, and this object here is what is going to be our conformal factor. Okay. Now, the space of meromorphic functions is a big space. So you should all be amused at this point. You should all be surprised, right? Because you learn that in d greater than 2, conformal transformations, infinitesimal conformal transformations, generated an algebra that was finite dimensional, right? And here it seems that we can use any meromorphic function. Okay? So given that you are not very amused, let's actually work out the generators. So if this is any meromorphic function, it admits a Laurent expansion. Okay? And let's actually see that we have an infinite number of generators. Okay. So the reason I decided to put this 1 here will become clear in a second, but let me justify it like this. It doesn't matter because, of course, we're summing over all possible integers. Okay. Now it's clear that the generators of conformal transformations will be related 1 by 1 for every possible monomial that we have in this expansion. Okay? So it's convenient to study them 1 by 1 as a transformation that is acting only on the holomorphic part and a transformation that will be acting on the anti-holomorphic part. Now, in this lecture, well, we can also write this. We can cut this time I'm going to spend writing on the blackboard by half if you're all willing to assume that every time I write something that is holomorphic, there will be something anti-holomorphic, okay? Maybe I won't do it all the time. Assume that you're willing to do that. So sometimes I'll write both things, but sometimes I'll just simply tell you that there is the anti-holomorphic part and just and avoid writing the whole thing, okay? So if this is a transformation, when we assume that all, so here what we're doing is assuming that all AMs are 0 except for M equals N, or except for AM. So the variation of Z would be this quantity, but this quantity has to be related to this. And it's given by this. Here I'm assuming that AN is infinitesimal. Okay? Very good. Now, in order to find the generators are supposed to be differential operators, right? In fact, they are vector fields. So we have to find a vector field. Maybe I can put this here, epsilon n. We have to find a vector field such that when we act with it, let's call the vector field Ln. When we act with it on Z, we get this object. Okay? So Ln is a vector field. And of course, it's very easy to recognize that it has to be this quantity. Okay? Now, for everything that I'm writing, as I said, there is an anti-holomorphic version, and therefore, there is also a var version that has the anti-holomorphic coordinates. Okay? So sometimes it will be convenient to represent derivatives with respect to Z just by a del, and derivative with respect to Z bar just by a del bar. Sometimes we will have different variables in the problem, so it might be convenient to just put a Z there or to put a Z bar. So depending on the context, we're going to be using all these possible notations. Okay? Now we have a set of vector fields, okay, for any n in the integers. So what do you think is the next step? Every time somebody gives you a bunch of vector fields, what's the first thing you try? Yeah, to commutate. Yes, to find the commutator. That's right. So that's the first thing that you should try, because you want to know if they become an algebra. Okay? So we have to compute this commutator and see what happens. Okay? So according to our definition, what we have to do is to take minus n plus 1 del of minus zn plus 1 del minus n plus 1 del zn plus 1 del. Okay? And do this calculation. Okay? So what do we find? Well, we find that if this derivative acts on this derivative, then it cancels the same term here, so that part is irrelevant. What's interesting is when this derivative acts on this, we should be an n and not an m. So how many of you noticed that? Oh, nobody. Oh, you did? I'll also do that now and then. I'll sprinkle typos, okay? And your job is to find them.
Then you should add the minus sign.
Very good, yeah. You see, it's working. Excellent. Okay, so we have Cn plus 1, this guy acts on this, and we get this. These guys combine to produce this, okay? And we still have this derivative. And then on the other side, we're going to get what? We're going to get minus, this is plus, and here we're going to have the opposite. M plus 1, Cn plus 1 plus n, del. And if I'm not mistaken, these should be, the ones cancel out, and this should be m minus n. And the minus sign works out precisely for this to be L plus n. Okay? If that didn't work, don't tell me now. Tell me at the end of the lecture. That's the other rule. Okay. So we find this algebra needless to say, but I'm going to say it nevertheless, we also have this algebra. Yes?
If you write, for example, in one generator, okay, transformation for Z, but you write, for example, transformation for Z bar in a different generator. And so does it mean that you transform Z and Z bar separately?
Well, that's also allowed. You can also guess exactly what's coming next. Okay? That's even more impressive than finding typos. Okay, that's exactly what we're going to discuss now. So, the first observation is that this algebra, well, it's not an observation. It's just seeing what's coming in the future. This algebra will be modified by quantum corrections, but what I want to say now is the following. This algebra looks exactly, if we treat Z and Z bar as independent variables, this algebra would look like the direct sum of two algebras. Okay? So if we were allowed to do that, to treat Z and Z bar as independent variables, then this object that we have found here is called the local conformal algebra. Okay? Would be isomorphic to the direct sum of two algebras. Okay? Each algebra generated by LMs satisfying this property. Okay? Of course, now the question is, are we allowed to do that? I mean, I'm very tempted to just go by, I mean, we're in a democratic country, right? So I will be tempted to ask if you think we should be allowed to do that or not, but given that these are my lectures, I get to choose. And the answer is that this is actually a standard trick. What's a standard trick? We're going to complexify space-time. So what does it mean? Well, that we take our coordinates, I'm using the same notation, x1 and x2, which were in R2, and now we want to think about them as points in C2. So we're complexifying both coordinates. Well, the advantage of doing that is that this immediately implies us that z and z bar are also coordinates in C2 because they are just related by a linear transformation. Okay? And this solves the deep puzzle of why I didn't call z bar z star, right? Which is the notation we all learned in high school. Hey, you probably wonder why didn't I use z star? And the reason is the following. The reason is that we're always going to think about C2, and inside C2 there will be a real contour. Okay? So if you have only one complex plane, when I talk about a contour, I talk about a real mid-dimensional cycle. Well, in any number of dimensions that would be true. But you're familiar with the case where you have only one complex plane, right? If I ask you to define a contour in a one complex plane, you will give me a curve, right? If I ask you to define a real contour in C2, what would you give me? Well, yeah, I already told you the answer. It's a mid-dimensional real cycle, okay? So in any number of complex dimensions, if you have a Calabi-Yau threefold, if you have any complex manifold, when we talk about contour, we can define it as a mid-dimensional real cycle, okay? So what would be a special contour in C2? What do you think? Special for its physical meaning. Well, a special real contour will be that defined by the following equation. And there you have it, your z star, okay? So z and z bar are independent coordinates, right? But this here defines a contour, a two real dimensional contour inside C2, okay? So I know it looks weird at the beginning, but let's go back to the case of one dimensions. If I give you the following integral, and I tell you integrate this, you would say, what do you mean? This is completely ill-defined. This is a holomorphic object. I cannot integrate this unless you give me a contour, right? So I'll give you a contour, and say I give you the contour defined by all z's separated epsilon from the origin. Now you can clearly tell me that this is equal to f of 0. Of course, if f doesn't have any singularities at the origin. And here there is another matter of convention, which is that when I have an integral, I really mean 1 over 2 pi I the integral. Okay. So that will also save a lot of writing. I don't know, I still haven't found any cases where where the 1 over 2 pi I is not needed. So let's stick to the convention for the time being. Now, how do we do it when we have two dimensions? So imagine we have an integral over two complex variables, z and z bar, of a function, again, of z and z bar. Well, in fact, let's come out with a particular function. Okay. Once again, if I ask you to calculate this, you would say, well, this is meaningless. Unless you tell me what the contour is. So here is an exercise. I'll give you two contours for this integral. And I want you to calculate what the integral is on both contours. So contour 1 is the following. So take C to be the set given by this. This contour is in fact isomorphic to T2, which is two copies of a circle, right? So the contour is a torus in a 4-dimensional real space. There is also something interesting that is fun to notice, that a circle, or in fact a torus, doesn't enclose a point in R4. So it's unlike the case of 1 dimensions where the circle encloses the point where you're integrating. Okay? But what the torus does is to encircle tubes of singularities that this function has. Okay? Well, that's not very important now. But so this is one of the things that I want you to try. And the other one is when C is contour 2. And guess what? Which contour am I going to pick? Clearly, our real contour. This contour is not isomorphic to T2. In fact, it's isomorphic. If you compactify the space, it's isomorphic to an S2. Okay? So I want you to calculate that in. All right. You know, it's funny, I was expecting 7 students. And all of a sudden, this is a... Okay, in any case. So, the first observation is that even though we're very happy to have our algebra as independent objects and a huge, huge algebra, we always have to keep in mind that we're doing things on the real contour, and that we are always want to go back to the real contour. So it would be interesting to know which operators preserve the real contour. Okay? So clearly, if I just take one of the vector fields, Lm, and apply it to my contour is going to be shifted, right? But if I take a combination of this form, this operator will preserve my contour, and therefore, it would be nice to keep in mind. Likewise, this operator would also preserve my contour. And especially when n is equal to 0, these operators will have a very particular meaning. But let's not discuss it right now, because first, let's discuss the difference between, or the reason I call that algebra, did I call it? Yes, the local conformal algebra. Okay, so let's discuss first the difference between local and global. So local here means that our vector fields are well defined on a particular open set of our space. Our space is a 2-dimensional space, right? So what is going back to the real slice, so the open space is R2, the open set. But let's think about this as a complex plane, C. Now, when we think about global, we want to think about the point at infinity as being a point that is a regular point. It shouldn't be special, right? More so in a conformal field theory. In a conformal field theory, we have inversions. So why would the point at infinity be special? So if we adjoin to this the point at infinity, we get a CP1, or a 1-dimensional complex projective space, But if you don't like that, this is just a two-sphere. Okay? So we want to find the objects that are defined on the full sphere and not on particular pieces of the sphere. Okay? So in order to do that, we have to consider the full vector field. In fact, this was completely planned. Okay? So let's consider the following general vector field. Let's use the full notation in this case. And ask, when is this vector field well defined? On my full S2, and not just on particular patches of our CP1. Okay? Well, clearly, there are only two dangerous places. Okay? Z equal to 0 and z equals to infinity. Those are the only two places where our vector field could do something strange. Otherwise, it looks very well behaved. So let's first ask for V of z to be regular at z equals to 0. So if we want the vector field to be regular at z equal to 0, all we want is these coefficients to be regular there. And that means that we want no poles, and therefore n can just be slightly negative. It cannot be too negative. So it can just be if it's negative, it can only be -1, right? Okay, that's very good. So what do you think the condition is when z equals to infinity? If we want this thing to be well defined at z equals to infinity.
And less than or equal to
Less or equal than -1. So that would mean that we have exactly one object, which is minus n equals to -1. That would be a little boring. Luckily, life is a little bit more interesting. And every time you want to test how an object behaves near a point, the best way or the clearest way is to go to local coordinates, okay? Where that point typically is at the origin. So we have to find a way to send infinity to the origin, okay? And then explore what happens when we do that. Now you would say, well, how would that change anything? I mean, this thing will still be the same thing, but now in the new local coordinates. But now we have this. This is a vector field. So the vector field will also transform, and this thing hopefully will help us get something interesting. Because if we only have one generator, the algebra will not be very, very useful. In fact, it would contradict what you guys learned in general dimensions. Okay, so now we want V of z be regular at z equals to infinity. So in order to do that, we have to go to local coordinates, meaning we have to go to another patch. And the patch is defined by a new coordinate related to the old one by this transformation. Okay? So what do we do? Well, we have to transform this to get the new vector field. And this object here is minus 1 over z squared, which ends up being minus w squared is. Now we can translate our vector field and write it in the new notation, in the new coordinates. And we get, well, we already know that n has to be greater or equal than minus 1. So we can just impose it there. And we get, so this coming from here, the minus sign, I don't care, right? It's not going to change our discussions. I mean, I'm not going to worry about this minus sign. So that contribution comes from there. And these two is the thing that is going to help us. Otherwise, we will be in trouble. Okay. Sorry? Here? No, this is still z. This is d of z, written in the other coordinates. Yes. So this new object is, we have minus m plus 1. And now we want this to be regular at w equals to 0, which is z equals to infinity. And that tells us that n has to be less or equal than 1. Right? Now it's looking good. Right? So we have n can take 3 values. All right. Again, this was completely prepared. So we can look at the algebra. With m and n in these values. And this is what is called the global algebra. Okay. Very good. Now, what is this algebra isomorphic to? Is this something that we have seen before? Well, why don't we try to identify these generators and see if we have seen them before? Okay. So, what do you think these generators are? Well, look at the definition. The definition of these guys is the following. This ended up being just a derivative, and this a del bar, right? So what do you think is the operation we're doing on our coordinates if we're only acting with those vector fields? We're just translating, right? So these are the generators of translations. And now to interpret the next ones, we have to look at the combinations that leave the real contour invariant. And as I promised, the case n equals to 0 was going to be important. So if you look at these ones, so what do these guys do? Well, they will transform z by something proportional to z with a factor, and z bar in the same way. Okay? And if we take A to be real, what do you think this is? We are scaling. So this guy deserves the name of the dilatation operator. Okay. Okay, so what's the next case? Well, as we saw before, we're going to consider this combination. And what does this operator do on our variable z? Well, if we multiply by theta, and we think about this as infinitesimal parameter, this operator does this, and this operator does this. And this is nothing but a rotation. Okay? If we think about our coordinates z, in this form, we can see that this will rotate z and z bar by adding a factor, a phase factor. Okay? Now, I decided to reserve the most exciting one for you guys. So this is an exercise. Show that L1 and L1 bar are generators of what? Of a special conformal transformations. Okay, very good. Now, if we put all these guys together as a variation on z, we discover that what we're doing is taking a variation of z that gives us three terms, three monomials with degrees 0, 1, and 2. So this is at most quadratic, okay? And now we want to guess, or we want to find out, what is the exponentiation of this. This is the infinitesimal version, right? And that's why we're talking about an algebra. Now we want to exponentiate in order to find what? What are we going to get here? We start with an algebra, we exponentiate it, and we find a group. Okay? So doing it this way might be a little bit hard, but I'm going to tell you the answer, and I'll ask you as an exercise to show that when you find the generators, you're going to find this. Okay? So if you exponentiate this, you're going to find that z goes to but of course, this doesn't match, right? Because I have 4 parameters here and you only have 3 parameters there. But there is a condition I haven't told you. And the condition is that AD minus BC is equal to 1. Okay? Now, your exercise is to go back. So what is this group? Well, you know what the conformal group in D dimensions is, right? So by analytic continuation in D, we should find what it is in D equals 2. So in D dimensions, you start saying Euclidean space, and a theory that is not conformal, but is just Lorentz invariant, has as a group SOD, right? If the theory is conformal, the conformal group becomes, you remember? SOD plus 1, 1, right? Now, as I said, by analytic continuation in D, so if you put D equals 2, you find SO 3, 1. But this object doesn't quite look like SO 3, 1. that object looks more like the group of matrices such that their determinant is equal to 1. So this group is called the special linear group of 2 by 2 matrices with entries in the complex numbers. Okay? Now, is this isomorphic to SO3,1? Probably. Yeah, probably. Or at least it should be related in some way, right? So in fact, as in terms of the algebras, they are identical. But globally, they are slightly different, okay? This group is simply connected, and this group is not. So we have to do something to this guy to make it look more like this one. But the answer is already here. Note that if you take any element of SL2C and you multiply by minus the identity, this object becomes the same transformation. So we have to identify those two. So for every M, we have to identify minus M with it, okay? In other words, both of them generate the same action. So the conformal group in 2 dimensions, or at least what we found over there, is not SL2C, but SL2C mod Z2, where this is a subgroup generated by the identity and minus the identity. And this is well known as a group statement to be isomorphic to SO3,1. Okay? So everything seems to be consistent. At least we're not doing something incredibly wrong. I am not. I should take the responsibility. Okay. So this is going until 8 o'clock, right, more or less? There is no local conformal group in higher, there is no local algebra in higher dimensions. Right? So you guys proved that without any doubt, right? You found the conditions for the vector field to be a conformal transformation, right? And you found that the transformation could only be at most quadratic, right? You guys did it, right? Excellent. Okay, so let's have a first look at the physical states. Of any conformal field theory in 2 dimensions. So, right. At some point, we're going to discover why L0 and L0 bar are going to be fundamental. And hopefully, we're going to discover that today. But for the time being, let's consider as a basis of our states. Basis will be eigenvectors of L0 and L0 bar. Okay. And we're going to call the eigenvalues H and H bar. And now we want these eigenvalues to be real. And the reason is clear. The reason is that they will have physical interpretations. Okay? So what is the eigenvalue of t? The eigenvalue of t is going to be h plus h bar. And the eigenvalue of the other operator, which is not here anymore, but is over there on the top there. And I didn't give it a name here. Maybe I should call it something like s. Okay. And the eigenvalue of s is h minus h bar. Okay. So this has the interpretation of the scaling dimension and that's clear because we interpret this, or we found that this operator was the dilatation operator, and this operator is a rotation operator, and therefore this combination is the spin of the state. Okay? Very good. Now we're going to move on to the part of the lecture that I can do in 2 minutes, because it's a fast review of things that you did in the past 2 weeks. In fact, you did it twice, I think. So why not do it 3 times? Okay? So let's move on from physical states to operators. In fact, as I said, we're going to review what happened in d greater than 2. And I believe you define the notion of quasi-primary operators. Is that right? No? Well, maybe you call it something differently. So let me tell you, it's an operator that transforms like this. Then you can tell me how you call it. Under a conformal transformation, it's an operator that transforms like this. How do you call those operators? Quasi-primary, right? Excellent. Yes. Okay. Now, remember, in d greater than 2, these guys are really global.
There are some characters that quasi-primary is more general than just primary. Is it true?
Well, let's see. So quasi-primary is something that transforms like this under the global conformal group, right? So in 2 dimensions, you can have objects, operators that transform like that under both global and local transformations. But you could also have operators that transform like that only under global and not under the local under the full local transformations. So what name do you propose? So the ones that transform like that for everything, local and global, how would you call them? If these ones are called quasi-primary, how would you call the ones that do something awesome? Primary, exactly, yes. Very good. So we just discovered why these ones are called quasi-primary. Because the other ones that are going to do even something better are called primary operators. So all primary operators are quasi-primary, of course, right?
I mean,
but not all quasi-primary are primary.
I usually mean the higher dimensions.
Well, this is the definition of quasi-primary in higher dimensions, okay? And any other operator in a conformal field theory is obtained from this by linear combinations and derivatives of these guys. And those, I mean, we can call them whatever we want, and we can call them secondary operators, right? Okay. Now, correlation functions. This was supposed to take only 2 minutes, and I'm... But But now you're experts in correlation functions, right? Especially 2 and 3 point correlation functions. You can now write them in your sleep, right? So if you have 2 quasi-primary with conformal weights delta 1 and delta 2, you guys found that this thing had no choice but to be 0 if the 2 weights are different from each other, and it was some normalization that we can choose, actually. We can normalize the fields so that this is nice. Where this thing is the distance between the 2 points where the operators are inserted, okay? You also computed, or you also determined the 3-point functions. And their life was more interesting because just by imposing translation invariance, Lorentz invariance, and dilatations, the answer was restricted to an infinite number of objects that you could write down, but it still was an infinite number of objects. And there was the first time where you had to use the full power of the special conformal transformations to get something even nicer. And this thing ended up being something that one has to work very hard to find, and which is precisely part of the definition of the theory. And here again, we have the distances. And this thing depends on the conformal dimensions. Okay? And for the 4-point functions, you realize that life wasn't as great because now you had something that could depend on what are called the cross ratios, which is the first 4 points is the first time you can make nice objects that are invariant under the full conformal group. And for 4 points, how many independent cross ratios are there? Do you remember? 2. So we can call them cross ratio 1 and cross ratio 2. Times something that, again, depends only on the distances, and it's not, it's interesting, but not so interesting for us at the moment, where this is the sum of delta I. Okay? Very good. Now back to 2 dimensions. So that was the review of everything you did in the past 2 weeks. No, I mean, you did much more than that. You found very, very interesting things about these functions. Okay, so now back d equals 2. Okay. So we start with the definition of a primary field. And that, as we said, is something that transforms like this for any function. Not only the global ones, but all the possible transformations. Okay. Now, why is this nice? Well, one of the reasons is that when you have a Riemann surface, you can define differentials. You can have holomorphic differentials, but you can also have quadratic differentials. In fact, you can have any power of differentials. And they give you a lot of information about the Riemann surfaces. Now you can define the H power of a differential, of a holomorphic differential. And the H bar power of the anti-holomorphic differential. And now our primary field defines a differential which is invariant. Okay. This will be much more useful when we have not a Riemann surface, not a sphere, but maybe a torus or a higher dimensional Riemann surface. Okay. But in any case. Okay. So what time is it? We have until 5. And you see, as I promised, the lecture was going to be very boring and nothing exciting, at least not yet.
But the exercises.
Yeah, but you have exercise, right? The exercises are the interesting part. But, I mean, why take all the pleasure? Right?
Label text, exciting.
That was also purpose. Okay. So let's look at what these guys do. Primary fields under. You see, it was so boring that even Gifre left. Okay. So we're going to take Z goes to this, where we are going to assume that epsilon is a function, but it's an infinitesimal transformation. Of course, we also have our friend. So what is the variation of our field? Well, we have two sources, right? So one will come from here when we apply the variation, and the other one will come when we expand the variation here, right? Of course, we're going to have 4, because we're going to do it for this, for this, for this, and for this, okay? But in the end, it's nothing but, so coming from this part, we're going to get H derivative of epsilon, and coming from this part, we're going to get a contribution of epsilon. The derivative now acting on the field, so I'm going to put the field here. Okay? And the same thing for the bar. Okay? So this transformation is going to be useful. Not today, unfortunately, but we're going to use it tomorrow. So it would be nice if you could derive it carefully, okay? So here I just told you where it comes from, but it would be nice if you could do it carefully. Okay. So once again, another exciting exercise would be to use these transformations to constrain the 2-point, the 3-point, and the 4-point functions. And I'm going to tell you what the answer is. So let me define some notation. So I'm going to say that Gn is the correlator of n primary operators. Okay, so that's a definition. And we want to write down exactly these conclusions you found in the general case, but now in 2 dimensions. Okay, so for the 2-point function, you should find, again, that this is 0 unless, well, every time these guys are different from each other. Well, in fact, in this case, it's easier to write first the other condition instead of this one, and then write the famous mathematician's way of saying something else. Okay? So it would take too long to write that. So the answer here is, again, a constant. And we have to introduce a notation. Cij is the difference of the coordinates, holomorphic or anti-holomorphic. So we have Zij if okay. Now note that if the spin is 0, right, then this object goes into something that looks like this, okay, which is a result that we had before.
Why is that C12 in that definition?
What do you mean, why is C12? C12 is just a constant that depends on the two operators. This is for 2. Yeah.
Oh.
That's right. Now the theory would be very trivial if all endpoint functions were as simple as this. Okay. Right. So we have that. Now we can move on and write the 3-point function. And again, it's going to be something nice. Times the same thing, but with the bars. Okay. And last but not least, and that's probably where we're going to end the lecture, is the following. So if we have the 4-point function, again, you would say, well, certainly we cannot completely determine the 4-point function. It has to depend on cross ratios, right? But note that there is something interesting that happens in 2 dimensions, and it's the following. If you take something like Z1, let me think. If you take Z13 times Z24, say you have 4 points, right? You take this. It's possible to prove that this thing is equal to Z12 times Z34 plus Z14, Z23. Okay? But this one is trivial. This is an exercise, but this is trivial. Okay? Can you see how this is going to happen? So imagine that 1 and 3 were 2 points and they were coming close to each other, right? So you get 0 here, and you get that this becomes minus this. So it's actually trivial to show that this is true. Now, why did I write such an identity there? Well, the reason is that, you see, if I divide everything by this quantity, what do I get? Yeah, here I get one cross ratio, here I get another cross ratio. But in fact, the one that I get here is the inverse of the standard cross ratio that you wrote down as the first entry as cross ratio 1. And on the other side, I get cross ratio 2. So in 2 dimensions, the 2 independent cross ratios that you had in higher dimensions are no longer independent. So this is great. So due to this deep identity, there is only one cross ratio in 2 dimensions. So we have to find a way to call it, and let's call it okay. So in 2 dimensions, we see our first simplification. We only have to find a function of a single cross ratio. And guess what? We have an infinite number of more identities, of more constraints, because coming from the local algebra. So we have less variables and more constraints. So that's where the power of working in 2 dimensions lies. Okay? And you won't believe it, but this identity actually has a name. I won't tell you a name. It's the name of somebody. Okay. So we have a little time. Yeah, 5 minutes. Many things have been discovered in 5 minutes. And the trick for the last 5 minutes is to use these flagpoints. So tomorrow, so I'm going to give you a preview of what we're going to do tomorrow. So tomorrow we're going to start the quantization, and we're going to study radial quantization. Okay? Now, why is it called radial quantization? The reason is that in a general quantum field theory, we can have UV and infrared divergences. So one of them gets worse as you increase the number of dimensions. And one of them and the other gets worse when you decrease the number of dimensions. Which one gets worse when you increase the number of dimensions? What do you think? Well, imagine the loop integrations, right? This all comes from doing loop integrations. So loop integrations in momentum space. If you have a fixed number of propagators and you increase the number of dimensions, you're increasing the power of momenta in the numerator. So when are you going to have a divergence? When the momentum is very small or when the momentum is very large? When the momentum is very large. Momentum very large means that you're in the UV. So these guys get worse for large t, and these guys get worse for a small d. So in d equals 2, you might expect to have very bad divergences. In fact, when you compute the propagator of just a scalar field in 2 dimensions, it doesn't even decay it goes like a logarithm, okay? So that's a sign that there are deep infrared divergences in 2 dimensions. So one way to fix that, which is actually fairly easy, so to fix that, what we do is, now imagine that, well, I'm going to change my notation as I promised. I'm going to call our coordinates in space-time sigma 0 and sigma 1. And what we're going to do is that we're going to identify this with this. So every point in R2 is going to be identified with an infinite number of images if you shift sigma 1 by 2 pi. So what do you think we're doing with that? Well, we're taking our sigma 0, sigma 1 plane, and every time there is a 2 pi separation, we're identifying a point here with a point here and so on. And therefore, this is identical, especially because these points are identified with these points, is identical to a cylinder. So we have sigma 0, the time coordinate, and we have sigma 1 as our radial coordinate, okay? So by doing so, we have solved the infrared problem. Yeah, if everything was that easy, it would be great. Okay, so I want to end today by doing the following. If we have a field theory on the cylinder, a standard field theory on a cylinder, that wouldn't be very useful for us. But if we imagine that we have a conformal field theory in the cylinder, then we can perform a conformal transformation to send the cylinder using a conformal map. We can take the cylinder into the complex plane. And what's going to happen is going to happen if we do the following. Let's introduce a coordinate W and W bar. And the conformal map will simply be an exponential map. Okay. So, in our new z-plane, 2 points are going to be special, 0 and infinity. So 0 will correspond to sigma 0 equals to minus infinity. So the point at minus infinity is going to be mapped to the origin of the plane, and the point at plus infinity is going to be mapped to infinity. Okay, so this one goes to z equals to 0, and sigma 0 equals to infinity goes to z equals to infinity. And lines of constant times here, surfaces of constant times, which are just circles, become circles here of different radius. Okay? Now, if you want to go from one circle to another circle that is slightly larger, what transformation do you have to do here? A scale transformation, a dilatation, right? But going from here to here means going from here to here. So you're actually changing time. So you're translating in time. So what's the interpretation of translation in time? So what operator does that in a field theory, translating in time? It's the Hamiltonian. And here is the dilatation operator. So we're going to have a map from field theories here and field theories here in which the dilatation operator actually becomes, well, it depends on where you start, right? But here I'm starting in the z-plane, becomes the Hamiltonian of the theory. on the cylinder. And that's also another reason why it was very important to have these eigenvalues to be real. Okay? And I think this is a good time, a good place to stop. So how many of you guys are also taking, no, all of you are taking statistical mechanics, right? Well, I mean, the Sci students, I mean. I see. Okay, and are you also taking quantum field theory 1? Okay. Good, good. Okay, very good, very good. So how many of you know path integrals? That's supposed to be in quantum field theory 2, but just asking. More or less. Oh, yes, yeah, but you have seen it somewhere. Okay. All right. Okay, so I'll see you tomorrow.